Example 2, we're finding they gave us, so we know what natural log of 17 approximates to. So I'm just going to go up to the point where we have it broken down to this, and you can plug it in your calculator, check your book. I'm just trying to make these a little faster since the last one did take 7 minutes. And your time is precious. All right, so because this is an exponent of my argument, I can move it to become a coefficient. So this is the same thing as saying 10 times natural log of 17. So in your calculator, you're typing natural log of 17 times 10, but they said without technology, so technically you are typing in 10 times 2.833, which is their approximation for your answer, and you should end up with 28.33. All right, part B, this is the fourth root is the same thing as saying 17 to the 1/4. Remember, rational exponents, they are key with logs. This is an exponent. I can move it to the front as a coefficient, so I get 1/4 natural log of 17. Again, do the same approximation with 2.833, and you get your answer. Example 3, rewrite them as a single number. These are fun. Sometimes they're confusing, but they are fun. Okay, log of 40 plus 2 log of 5. Notice I'm skipping it out on saying the 10 for the base because it's already assumed you don't see it. The base has to be 10. All right, so this 2 is actually an exponent. 5 I can't break down any farther, but 40 I could break down with the 5, so I could do log of as a single number. Wait, they're all the same base. Okay, never mind. We'll keep the log of 40. This exponent will come back up on top, so this is plus log of 5 squared. And now since they're being added with the same bases are key. If you don't have the same base, you can't do squat. This is 40 times 5 squared, and 25 times 40. 25 times 4 is 100, add an extra 0, so it's 1,000. So this is a log of 1,000. And what is log of 1,000 actually? 3. Do they actually give it? Oh, they don't actually want us to find us the number, but hey, you could actually find log of 1,000. Okay, and then part B, this one's fun. It's base 2 of 3/5 plus log base 2 of 5/2 minus log base 2 of 3. This is where it's confusing because you see the division here because of the subtraction, but you see multiplication here because of the addition. So it means for you to do it from left to right because that's how you add and subtract with order of operations is from left to right. In the question on the homework answer for this question that's in the homework, I purposely put parentheses around the addition because I wanted that to be done first. So just watch out for order of operations. I know it's funky, but they all have the same base, which is awesome. These are being added, so I mean they're actually being multiplied. So I get 3/5 times 5/2, and then this is all going to be divided by 3. So that's all in the argument piece of this log. 5 divided by 5 makes 1. 3 and 3 makes 1. So I'm going to end up with log base 2 of 2, which should equal 1 if you fully simplify. All right, example 4. Example 4 is to rewrite 1/3 natural log of t plus natural log of 5. So natural logs are the same things as regular logs or base 2 logs, any log, because they have base e. So rewrite this, I can do natural log of t to the 3rd plus natural log of 5. Same base, they're being added, so I'm actually going to multiply natural log of 5 t to the 1/3. Yep, there we go. Example 5. Okay, this one's funky. So that number there was the largest known prime when it was discovered in 2006 by a greatest internet mersenne prime search. So there is a rule where 2 to the x minus 1 will be a prime number, and then you just have to find out. It's not always going, does not matter, like not every exponent will work. So in this case, if x was equal to 4, I get 2 to the 4th minus 1, so that's 16 minus 1, so that's 15. 15 is not prime, but all primes will follow this pattern. It's just not every number of this pattern is a prime number. So when it was discovered in 2006. So they found this number in 2006. Did they win a $100,000 prize for finding the largest known prime? There is a homework question number 12. They discovered another prime in 2008. So we are assuming that it is prime, like they discovered it's prime. But on 12, when they ask, did it win the prize, they're asking, is this prime larger than the prime from example 4 or 5? So look at the digit numbers for that one. So they want to know, is this large? Okay. They are okay. The key piece of information is above in the paragraph above on page 591. One of the uses of a logarithm of power is to estimate the size of numbers that are too large for even many calculators or computers to write out. Because if you tried to do this problem on your calculator, you'd get overflow. In 1999, the Electronic Frontier Foundation announced a $1,000 prize to the first person or team who found a prime number with more than 10 million digits. So we're looking for digits to be more than 10 million, okay? So we know the number of digits can be found by finding the common log. Another way of looking at this problem is, I'm going to go back so I have more space, is to look at the we're going to let x equal the number 2 to the 32, 582, 657, and yeah, okay. So we're letting this be the number. We actually care about this number. So if you have 2 to some exponent, it's huge. So this number will be huge. It's not just a double-digit number. It's a huge digit number. If I subtract 1, is that going to change the number of place values that I have? No. So if I find the number of place values in just this number, I'm golden. So so I'm going to try to find the place value of this number. If I take the log of both sides, 2 to the 32, 582, 657, now I've taken the log of it, so it's the common log of x, which is what I want. This is going to equal the number of digits, rounded up. It'll be equal to the number of digits that x actually has, which then in turn is the number of digits that has. So if I want to find this, this is a base, this is an exponent, so I can move that exponent to the beginning as a coefficient, and now my log for my calculator is just log base 2. This will give you an overflow, this does not. So, in your calculator, type in this whole thing, 32, 582, 657 times log of 2. Woohoo! Okay, so this gets us 9808357.095. If it's an approximation, use your squiggles, but this one's exact. All right, this rounds up to 9808358 decimal places, so it should, right? Are they rounding it up for me for that? Yeah, they rounded up. So this is 9,808,358. 9,808,358 place value or digit number. Is that more than 10 million? No. So did they get the prize? No. This is just how many digits there are. I do want to continue with what the rest of the book goes through. So they're using, we now know this. What base is this? 10. So I'm going to have 10 to the power of 9,808,358. That actually is my mysterious number. Okay? So you could write it like this. Well, I guess we're on this right now. You could write it like this, or you can write it like this. Both of those are the same number. And, I'm going to actually keep the decimal, because that's important. Keeping the decimal. So now it's still exact, so I'm using my equal signs, and it's important because now I can write this as 0.8357 times 10, 0.095 equals x. Remember your exponent rules from years ago. If I have a base at the same base, if I multiply them, that's adding their exponents. Adding these exponents gets this upper exponent right here. This I don't really care about. I can leave it as is. So I get 10, 9, 8, 0, 8, 3, 5, 7. This is small enough, I can actually do that in my calculator. And I'm going to get 1.24451612. We can make this approximation. And what does that look like? Scientific notation. Boom. So that's why this rounds up to 8 for digits, because that 1 is your extra digit. And so your common log will always round up 1 to get your digit number. And this is your scientific notation. So I actually know what the beginning of this number looks like. The first digit is a 1. The second digit is a 2. Third digit is a 4. 4, 5, 6, 1. I don't know that one because that one is a 2. But it goes on forever for this many digits. I just know the beginning few of them. So that's really cool.